Kia ora, everyone. My name's Nicol. I'm from the University of Canterbury, and it's a great pleasure to talk to you today about earthquakes and faults. Before I do that, I'd like to acknowledge that the Royal Society, and thank them for inviting me to become a fellow, and also I'd like to acknowledge multiple generations of family and colleagues that have helped me get to where I am now. So today I want to talk about earthquakes, something that if it's not dear to your heart, it's certainly relevant if you live in New Zealand. And I'm going to talk about it from the perspective of how earthquakes actually accumulate on faults to produce what we call fault growth. And I'm going to talk about this from a New Zealand perspective and become clear why I'm doing that in a moment. On the first slide here, we can see we've got a number of pictures, which are basically the consequences of the Kaikoura earthquake in 2016. So when we think about earthquakes, they actually occur on faults, or what we often refer to as fault lines. So these are surfaces, usually in the upper part of the Earth's crust, so they're plains, and they accumulate displacement. So they have some displacement of markers on them, which happens during earthquakes. So if we look at the figure in the top right there, we can see some faults in a road outcrop. And we can see the beds there, which are sedimentary beds, have been displaced by the faults. And that displacement usually accumulates during earthquakes. So that's what actually happens during earthquakes. If we think about the fault lines that are probably most famous or dear to our hearts, on the left-hand side there, we can see the San Andreas fault. You can picture Dwayne "The Rock" Johnson flying along that immediately after it's broken in a big earthquake. That's probably the world's most famous fault line. And then possibly for us, or at least people living in Wellington, I've got the Wellington fault in the bottom right there, where you can see it going through Zealandia and close to the western edge of Wellington City, and then up through the Hutt Valley there. And the vertical red arrow there is the Royal Society of New Zealand. It's just down the road from Parliament. I'll talk a bit more about the Wellington fault later in the presentation. It's quite common when we think about faults to just think about individual structures. The Wellington and San Andreas examples I showed you before were individual faults, but actually it's actually useful to think about faults as a collection of structures or a network of structures which are all interacting with each other on a range of different timescales. And that includes the earthquake timescale. So when we have an earthquake that produces slip on a fault, that fault interacts with the nearby structure. So we have a system of fault lines, and they're all essentially communicating and working together. Now, Aotearoa New Zealand is a good place to look at faults and earthquakes, largely because we have a lot of both of them. The reason for that is that we sit on a plate boundary, the boundary between the Australian plate and the Pacific plate. So on the left-hand side, you can see the figure that shows that plate boundary. We've got roughly 40 to 50 millimetres a year of motion between those plates, and that's taken up by convergence, so the plates moving towards each other, and translation, so the plates moving past each other. And as a consequence of that, the crust in New Zealand gets stressed, and as a consequence of that, the crust will break in earthquakes. On the right-hand side, I'm showing the locations, the epicenters of earthquakes from 1843, just the on-land earthquakes and the shallow ones, and that really just illustrates how important these earthquakes are for Aotearoa New Zealand. I'm going to talk mostly about the earthquakes that are plotted on the right-hand side here, and we will kind of think about what we see in those earthquakes and what that tells us about faults and how they grow. Here's a map of the Kaikoura earthquake. The red lines in here are the fault lines that ruptured during the Kaikoura earthquake. The key thing to note here is there are lots of them, and it's quite complicated. This earthquake has become a bit of a poster child for earthquakes worldwide, in that it ruptured many faults, and they have different orientations and different types of slip. The question here is that is this a common feature or not? And even though this type of multi-fault earthquake was kind of really popularized after the Kaikoura earthquake, it seems like there's evidence to suggest it's more widespread than that. So here we've got a nice picture of the surface rupture at Waiau from the earthquake. That's a 3-metre high wall that just rose out of the paddock. And on the top graph there, I'm showing the magnitude, so the size of the earthquake, and time on the horizontal axis. And the key thing to note there is that all of the sticks with red circles on the top, they are earthquakes that happened and produced rupture or slip on multiple faults. So the key takeaway here is that it's very common in New Zealand, and actually worldwide, to have earthquakes that break more than one fault, and that's another piece of evidence to suggest that there's quite close interaction or communication between the faults, sometimes on the time scale of seconds or a few tens of seconds, and that's essentially what happened in 2016. Now we can dig a little bit deeper into that earthquake data set, and I'm going to show you 3 graphs to kind of finish up here. Really what I'm trying to do here is trying to figure out whether there's any relationship between the size of the fault and how quickly it grows and how it grows. So on the graph on the left-hand side, I'm showing length, and that's kind of my measure of size. So bigger faults are further to the right. And on the vertical axis there, I'm showing slip rate. So that's a measure of how fast the fault might grow. The red symbols on there are information from New Zealand's earthquakes since 1843. And what you can see there is that there's a general trend of the data. So what that means is that longer faults generally grow faster. If we look those lines there that you can see with years, 100,000 through to 100 years there, those are contours of the time between earthquakes. And what you can also see is that the bigger faults have more frequent earthquakes on them. If we turn our attention to the graph on the right-hand side, there we're showing the length of rupture during the earthquake on the vertical axis, and on the horizontal axis we're showing the geological length, so the length we measure in the rocks. And that line on there, that diagonal line that goes up the graph, that's the 1-to-1 line. So in other words, if the earthquake ruptures all of the fault, the symbol would sit on that line. And what we can actually see is that it's common for all of the fault surface to be ruptured in an earthquake, about a third of the time. But for 2/3 of the time, the earthquake ruptures a part of the fault line. So it's kind of picking up bits and pieces of fault lines of different faults during the same earthquake. Got one more graph to finish with here. What I'm trying to do here is to try and understand how many earthquakes it takes to grow a fault. And so what we've done in this graph is we're plotting displacement. So thinking about that picture in the beginning, so how much displacement of the bed have we got, and the length of the fault, okay, which is how long the trace is at the surface. And I've got 2 sets of information here. The red symbols are what happens in individual earthquakes, and the black symbols are what happens when we accumulate those earthquakes over many thousands, tens of thousands, or millions of years. What you can note here is that the trend of the red symbols is shallower than the trend of the black symbols. And what that means is that if we have a short fault with a short length, it generally accommodates less earthquakes than a long fault with a long length. And I've put in here, just to go back to the Wellington Fault, which is where we started, I put the Wellington Fault on here. It's that deep blue symbol there. And what we can see when we're looking at the Wellington Fault is that using this type of analysis, it would take roughly 1,000 or more earthquakes to generate the slip we see on the Wellington Fault, and that would happen over, if it's a constant process, that would happen over a period of bit over 1 million years, and that's about 4 times longer than humans have been on Earth. So the idea here is that faults take a long time to accumulate their displacements, way longer than the human lifespan, or even the span of the Homo sapiens on Earth. So we're almost finished. Just to conclude, to wrap it all up, we're thinking about earthquakes, we're thinking about faults, think about them as interconnected, interacting networks. And that interaction is partly why they're so complicated, and partly why it's taken a while for us to understand exactly what to expect in the future. When we look at the earthquakes we've had, they tend to be multi-fault earthquakes. They rupture parts of faults. And what tends to happen is the bigger ones grow faster than the smaller ones, and the number of earthquakes that you need for those bigger fault lines is increasing as well.